we're going to continue, and I'm going to show you the procedure with this example that I shared with you. Are you seeing my screen, people? My PowerPoint presentation? Somebody check? Okay, thanks. So here we have the whole thing. Let me go back. So this is a combination now. Okay, this is a vertical element, like a tube. This is a cable, another cable. And let's suppose that here we have a weight that we want to lift. Okay, since you see that these are pins. Okay, the connection between them can be considered as bars. Okay, so there is no bending in this case. For example, for this element here, we do not consider its weight. If we included its weight, then this element would be a beam. No, we want to consider only, chapter 1, only bars. Okay. Of course, you can immediately see that you have 1, 2, 3, and 4 bar elements. And since we have a load here, an external force here, this force could be easily represented or applied in this joint. So this is the discretization that we're going to use. So we have joint 1, 2, 3, and 4, and we have 1, 2, 3, and 4 elements. The value here, this is the force that I think it's the equivalent to this one. This is 5,000 pounds. And on the right, I have the equivalency in international units. These are meters. So we have everything ready. So let's go. The element one. So it goes from here to there. Okay. So this is element 1. So you can see that the local reference system, see? Here, I'm sorry, here I have the global reference system. So this is theta 1 for this element. So more or less is 45 degrees. That is the value that you see here. Then you have the area, and you have these values, which is going to be common to this element. Element 2, people, somebody, element 2, you see here, element 2, and you see that it is defined in this example that going from 2 to 3. Question for you, how much is theta 2? People, tell me, how much is theta 2? Anybody? How much? How much is? Exactly. So you can try to write it here. So you have this is my x2. And of course, this is going to be y2. And you see that you have rotated from here to here, because that's the global x direction. But this is the opposite direction, right? Because this is the z. So I'm sorry. There is an error here. Let me correct. Yeah. The local, I'm sorry, the local is defined from the global to the local. So this is theta 2, Jesus, there. But this is opposite because it's counterclockwise, I'm sorry, this is clockwise. This is counterclockwise. So this is going to be equal to minus 90 degrees. So here is minus 90 degrees. Okay, and again, for the element 4, you see here, I'm defining it from joint 2 to joint 4. So this is, let me change color, see, that helps. See, I go from here to this direction. This is local 4. There. Okay, so this is going to be my theta 4. So probably give me a guess, people, somebody? A guess for theta 4?
60. Minus 63.
How much? How much?
The same on the tree, but negative.
Minus. Minus. Be careful, because this is clockwise. Clockwise. And you are going in the clockwise direction, that's negative. So be careful, please. So it's going to be minus the value, you have to do it at home. Okay, something.
Doctor,
Yep,
I have a question.
go on.
What happens if I define the direction of local reference system in another direction, or I should
No,
follow the young?
there is no problem at all. At all. See, you could define, for example, you could define the reference system of the second element like this. Okay, that's going to be your local reference of the second element. But you have to be careful because the first joint of your element is going to be joint 3, and the second joint is going to be joint 2. So when you form the global matrix, stiffness matrix, you have to be careful who is your first and who is your second joint. That's all. That's all. Okay, there's no problem. You have to be careful. That's all. Okay.
So in the blue reference system, I have changed the joints, right? The number of joints.
Exactly. Exactly.
Okay.
In the blue, in this one case, what you're saying is that, remember, each joint will have 2 forces, and here we have 2 displacements, right? So in this case, you're saying because this is depends on the engineer. So this is your first joint, right? So this is joint 3. So here you're going to have F3x, F3y. And the second one is going to be F2x, F2y. Here, similarly, D3x, D3y, D2x, D2y. So when you combine, because you see that there is a common joint here, you combine that, and also there is that's common joint. And in this case, you have to be careful because you have to take this component, which is this part here, because this part here is relating to the force in joint 2. Okay, that's the, you have to be careful with that, but that's all. You can define any way you want. Okay?
Okay, doctor, thank you.
Okay, no problem, no problem. Let's go on. For each element, remember that we do this for each one, but this is local reference system, local reference system. And then for each element, we do this, okay? And then this is the result that I wanted to show you, okay? So for each one of these, this is this matrix that you see here. This is the result of multiplying T transpose times K in the local reference system times T. And here you have your theta I. Here you have E A over L of each one of the elements. So you multiply all of this, and at the end, you have all of this. So you have the EA over L is here, and since here you have the angle, cosine, sine, and this is the result. You don't need to learn this by memory. You don't need, if I ask you to do this, to do an example or a problem like this in an evaluation, I will give the matrix, don't worry, okay? But you have to be certain that you recognize where did you get, how did you get this matrix? Questions about this, people? Okay, so that's how do we get it. So in this case, this is the result for the element 1. So here we have the value of EA over L, that's the term outside. And here is the result, considering that theta was plus 45. So this is the evaluation. Remember, bar 1 relates joint 1 to joint 2. We can do the same for all these 4 elements. Okay, and now we are ready to go on with the combination. Okay, we have to be careful about the units. So EA over L, here, these are the units of E. These are units of L, and this is unit of length. So the result is going to be F divided by length. So you multiply this, any one of these matrices by times D, and the result is going to be force, as it should be. Now, let me finish today with this continuity. Remember, right, in this point here, okay, D2 is this one. For the element 2 is this one. And for element 4 is this one. This value is equal to that, is equal to that, in order to have continuity. Okay, so we have to recognize that. And consistency, that means that if I have a force here, let me explain it like this. I have this is the total external force that I have here. This is F2x. Now, what we do is we split like this. So a piece of that is going to be required in order to keep this element in equilibrium. See? The rest is going to be for the second one, and the third part for the third one. But if you add the 3, you have to recuperate the total force. What is the total force that you apply in joint 2, people? What's the total force that you apply in joint 2? Somebody?
0.
Exactly. Exactamundo, 0. That's the total external force there. That means that, of course, when we don't know something, we have to assume in the positive direction. In this case, these directions are not correct. Okay? Probably this will produce tension, this will produce tension, and they will oppose each other. And that will cancel because the total force has to be 0. That's what we're saying here. And with this, we go on. Remember that we have to go in X and also in the Y direction for each one of the 4 joints. That's equilibrium. Remember, discretization means that we only are worried about what happens in the joints. So what we do is we split each one of these matrices in 4 pieces. So this is multiplied by the first joint and produces forces in the first joint. This is multiplication of the second joint and produces the contribution for the first joint. Similarly for the second forces. Okay, now this is the first element. This is the fourth element. Okay, and we see that this is the second joint is common. So this part here has to combine with this part here. Okay, now we have to remember that this first column is multiplied by joint 1, and the second is multiplied by joint 2. This part here is multiplied by joint 2, and this part here is multiplied by joint 4. So what we have to do is we can, if this is a global, I'm sorry, this is a global stiffness matrix, you see that it's full of zeros. Okay, again, we split it in forces in joint 1, 2, 3, and 4, and columns multiplied by displacement in the first, second, third, and fourth joints. You see that this belongs to here. This belongs to here because it's relating joint 1 and 2. And this one here, you see that this relates force 2 and multiplied by the second displacement. But this one here is second force, but multiplied by the fourth displacement. So it goes here. This one here, and the rest one has to be here. In this way, we are contributing from the from each one of the elements into the global stiffness matrix, like this. So at the end, this is going to be the result. You see here, for example, that this space is full of zeros. Why? Because this is expressing the force in the first joint. This is the first joint. But because of the displacement of the third is here. So they are not related. That's why this has to be 0. At the end, this is the result. I don't know if there is any question, people. No? I would ask you to complete this example. And then on Monday, we can go on and see if there is any questions about this, okay? Remember that after you solve for the displacements, you have to go on, and for each element, you have to calculate the stresses. So in this case, what you need to do is you can, since you have this vector here, you're going to apply this transformation to calculate the displacements of every joint in the local reference system. With these values in the local, you can calculate strains, stresses, and internal forces. This is what we're doing. And then you have the forces, internal forces in the four elements. And then it's always a good idea to calculate or to establish the equilibrium. In this case, we have the forces in this joint, and you see that this points to the left, point to the right, and also have components downwards, which cancel this one. So you can see that this joint is indeed in equilibrium. Oh, this is some. So please review this example over the weekend. And if you have questions, I will try to solve them on Monday. Any questions about these, people?
Doctor, good morning. My last name is Diaz. I have a question, but it's about the vibration mechanics.
The what? No.
Vibration, no.
No. This is just finite elements, people.
Okay,
Don't get them. Oh, yeah. Please. Everybody has to print or capture the page in the syllabus, and you have to sign it, and you have to send it to us, because we need a proof that you received the instructions on the syllabus. I don't want to be, but I can do it. For example, I could get the point where I said, if you don't send me that, I'm not going to give you the the quiz. So I don't want to reach that point, but I can do it. Second, vaccination certificate. We're completing the second week. Remember, at the end of the fourth week, you have to come to get the evaluation in person. But we have to be certain that we don't have anybody who brings the disease up to the point where we can control. So we need a certificate. The certificate is so simple to get. You get into that website, download it, and send it to Loyola. That's all. You don't need to print. You don't need to pay. That's all. I urge everybody to get the vaccinations, get this certificate and send it to us. Please, put you in my shoes. We're going to be 35 people in one room. Well, not in one, in 2 rooms. We have to be certain that everybody has received the vaccinations. Bye-bye now.
Thank you, Doctor.